Hello. Okay, here we go. Let's take a look at this thing here. So we have a function f changes values when x changes from x naught to x naught plus delta x dx. I'm sorry. Find the change delta f. Okay. The value of the estimate of the change, which is given by df, and the approximate error. No, in other words, how bad is the guess? Okay. Or the approximation. Okay, so here we go. So first we find, y equals f of x. So normally, well, I'm going to call it dy. Okay, in our situation, it's the same as df, right? But I'm going to call it dy as well. So first I have to differentiate the function. So I get 16x plus 7, and then I have to multiply by dx. Okay. So let's see what we have here. Now in this situation we're interested at the point x naught. So I'm going to write down df is exactly equal to, in this case, at the point x naught equals minus 2, so we get 16 times minus 2, right, plus 7, and then we have times our dx is a change in x is 0.1. So notice that in a sense dy is a function of dx and x. Okay, so that's our dy. And let's see, for this one, I know that we're not using, any sort of calculators or anything on our exams, but for this particular problem, feel free to bring out some technology. Let's see what we get here. So this is, negative 32 plus 7 times 0.1. Well, this will be easy. So this is a negative, 20, so if I add 7, negative 25 times 0.1. So in this case I can do this without any, so it's negative 2.5, right? All right, so that's our dy, right? Now the first thing we want to do is approximate, okay, so we found the value of dy, right? Let's find the change f of x naught plus delta x minus f of x naught. Okay, so the what we're looking for here, what is the actual change? Okay, well the actual change would be f of let's see, we're going x plus delta x, so that would be a negative 1.9, right? And then we want to subtract f of negative 2, okay? And let's see what we get here. Oh, I'm going to drag my calculator out because I'm just totally lazy. Maybe a different one. I like these. See, a really good technology. As a little side note. If you're going to use this stuff, I have to make sure I can see what it is that I'm evaluating, okay? So what I mean by that, watch this, you'll actually see this appear. And then, so it's a good way of sort of mitigating the accumulation of errors, okay? So I'm going to take that times, so what am I doing here? I have a negative 1.9, and then I'm going to be squaring that, okay? And then I'm going to be adding, okay? What am I adding to that? So now I'm evaluating the function at negative 1.9. So 7 times negative 1.9, 1.9, right? So good. And then I'm going to be subtracting, right, what I get when I evaluate at negative 2. So it's going to be 8 times negative 2 squared, and then we're going to be, where's my function? Okay, adding, well, I can see it right there, adding 7 times a negative 2, and I'm going to just finish off the parentheses so that everything is well defined. And there, look how you can just see it right in front of your eyes. So I confirm that that's correct. And what do we get? So if we do this, find the actual change, we get a negative 2.42. So this is negative 2.42. Okay, so then what's the error here? So if I look at the distance from these two things, all right, what do I get? That's the absolute value of a negative 2.42 minus a negative 2.5, right? And that's going to be what? Well, it looks like it's going to be 0.08. Right? Does that make sense? Or yeah, I guess that's correct, right? So you have the 2 and then 0.42 from 0.5, so you get 0.08. So that's the error. That's how far off we were by approximating the change using our differential. So I hope this helps out. Thanks.